So let's work some additional practice for Chapter 6. So remember, Chapter 6, Module 6, whatever you want to call it, it's all of your gas laws. So we're dealing with two different gas constants here. We're dealing with different units of pressure. We're looking at converting volume, temperature, Dalton's law of partial pressures, your velocity, kinetic energy, etc. Lots of things going on in this chapter. First example, what pressure will 14.0 grams of CO2 exert in a 3.5 liter container at 75 degrees C? So I want to know pressure. I've got 14 grams of CO, 3.5 liter container, and 75 degrees C. For this, I'm going to use the PV equals nRT equation. P is what I'm trying to find. V, 3.5 liters. N, I'm going to calculate. I've got 14.0 grams of CO. Convert that to moles of CO. Carbon monoxide has a molecular weight of 28.01 grams per mole. So I have 0.500 moles of CO. And my temperature, 75 degrees C. Convert that to Kelvin, would be 348 Kelvin. So, rearrange your equation. P equals nRT over V. 0.500 moles times 0.08206 liter atmosphere per mole K. 348 K. Oops. Divided by our volume of 3.5 liters. Final answer here, our pressure will be 4.1 atmosphere. So just to make sure, your moles cancel with your moles, liters with liters, Kelvin with Kelvin, we're left with atmospheres. And we have 2 sig figs here, so I will have 2 sig figs in my final answer. So 14 grams of CO in a 3.5 liter container at 75 degrees degrees Celsius will exert a pressure of 4.1 atmosphere. What is the molar volume of an ideal gas at 760 torr and 546 Kelvin? So a few different ways you can solve this. You can remember what STP is. STP, 1 atmosphere, 0 degrees C, which is 273 K. You can recognize that this is double my temperature at STP, and 760 torr is equivalent to 1 atmosphere. So you could recognize that, oh wait, my pressure is the same, my temperature is doubled. I know that temperature and volume are directly proportional. I know that 22.4, let me find a color you can actually see here, I'm sorry. 22.4 liters is molar volume at STP. So since I doubled the temperature, I expect the pressure or the volume here to be double as well. That should be 546 K and 1 atmosphere. The other way to solve this problem, though, is to recognize what does molar volume mean. Molar volume means the volume of 1 mole of gas. So if I'm looking at PV equals nRT, I want to find volume of 1 mole, gas constant 0.08206 liter atmosphere per mole K, temperature 546 K, and pressure 760 torr, convert to atmosphere. And I'm going to get 44.8 liters. So you can solve it one of 2 ways, but 44.8 will be your answer here. Determine the volume of SO2 at STP formed from the reaction of 96.7 grams of FeS2 and 55.0 liters of O2 if the O2 is originally at 398 K and 1.20 atmospheres. Lots going on in this question. So first, trying to find volume of SO2 at STP, which means 1 atmosphere. 0 degrees C, or 273 K. I'm reacting 96.7 grams of FeS2, 55 liters of O2, and the O2 is at 398 K and 1.20 atmosphere. So I've got 96.7 grams here. And how much O2? Well, we're going to have to figure out how many moles of O2 we have and how many moles of FeS2 we have. This is a limiting reactant problem. So if I have 96.2 grams of FeS2, how many moles of O2 are required to completely react all of this? How am I going to go about that? Well, convert through. See what it tells you. How many moles, or in this case, I'm going to go to moles since I'm going to find moles from the ideal gas law. You can also go to grams if you want to, but how much is actually required? So I want a number of moles of O2 to react all 96.2 grams of FeS2. So, okay, 96.2 grams of FeS2, convert that to moles of FeS2. If you add up the molar mass of FeS2, you should get 119.99 grams. You could round that to 120, just put a decimal place at the end if you want to. I just like keeping things not rounded until the end if possible. I see 11 moles of O2 are required to react 4 moles of FeS2. I would need 2.20 moles of O2 to completely react all of my FeS2. So this is what is needed to react all of my FeS2. Do I have enough? Do we have enough O2? Well, I don't know yet, right? We got to calculate the number of moles. Number of moles of O2 is equal to the pressure of O2, so 1.20 atmosphere. The volume of O2, 55.00 liters, divided by your gas constant, 0.08206 liter atmosphere per mole K, times your temperature, 398 K. Atmospheres have canceled, liters have canceled, Kelvins canceled, moles in the denominator makes a numerator. My number of moles of O2 is equal to 2.02 moles. So do I have enough? No, I don't. What this means is that we don't have enough. I'm going to move this up just a sec so I can write. We do not have enough O2 to completely react all of my FeS2. Therefore, O2 is my limiting reactant. So the moles of O2 I have will determine the final volume of SO2 I can actually produce. The moles of O2 are going to limit how much SO2 is produced. So number of moles of SO2 produced will be based on the number of moles of O2 I have. 2.02 moles of O2. I see I produce 8 moles of SO2 for every 11 moles of O2 reacted. This gives me 1.47 moles of SO2. Now I can go ahead and convert this to volume with my ideal gas law. It does tell me I want to know this under STP conditions, so I do have to remember STP now. Solve for volume of SO2 produced. We've got 1.47 moles. My gas constant, 0.08206 liter atmosphere per mole K. Temperature, 273 K. And my pressure, 1 atmosphere, because I'm at STP conditions, 32.9 liters, and that is of SO2 that can be produced. So again, we can do limiting reactant problems a lot in thermo and in gas laws. We saw this now with calorimetry. We've seen it with just reactions in energy, like stoichiometry when it comes to thermo. We could use Hess's law to figure out delta H of a reaction and then use limiting reactant problems. We've seen it with production of H2O when we're collecting gas over vapor. Lots of applications. Limiting reactant comes back heavy throughout the rest of our semester, so please don't forget that part. Okay, number 4. A sample of gas occupies 8.5 liters at 23.0 degrees C and 734 millimeters of mercury. What must the pressure be in order for this gas to have a volume of 12.0 liters at 23 degrees C? So, I've got 8.5 liters, 23 degrees C, 734 millimeters of mercury. I want to know what is the pressure if I change this to a volume of 12 liters and 23 degrees C. This is your combined gas law. Again, I don't really remember the combined gas law. I remember PV equals nRT. I solve for R, PV over NT under one condition. R is going to be the same under the second condition. Like R is a constant. So P2V2 over N2 T2. These have to equal each other. This is what we call your combined gas law. And in this question, we talk about liters, temperature, and pressure. We do not mention moles, which makes me assume that moles is held constant. So I've got P1V1 over T1 equals P2V2 over T2. My volume is in liters in both. My temperature is in degrees Celsius in both, and I'm trying to find pressure. Now, you can go ahead and convert everything to your proper units, but because a lot of things are going to cancel, I'm not going to have to. My pressure is going to be equal to my first pressure times my first volume times my second temperature, divided by my T1 times V2. First pressure, 734 millimeters of mercury. It doesn't specify what unit my pressure needs to be, so I'm going to leave it in millimeters of mercury. V1, 8.50 liters. And temperature, 23.0 degrees C. Normally, you would convert that to Kelvin. And if you want to convert to Kelvin, please do. But if I convert to Kelvin, it's going to be the same value. The temperature has not changed here. You could actually leave temperature completely out of this equation because the temperature is constant in both. So I didn't think about that. You could actually just do this and leave temperature out entirely if you'd like. Because temperature stayed constant, I can do this. Either way, you can solve it with or without. It's going to get to the same point. Pressure here, 520 millimeters of mercury. And if it asked you for this in atmospheres, we know 1 atmosphere is 760 millimeters of mercury. This would be 0.684 atmospheres. So whatever units it wants to ask you. Again, you could leave temperature in there like I originally had it because it's 23.0 degrees C. In both of them, it's constant, so I'm just not going to even include it and risk putting it in my calculator and getting a different answer because I don't type something incorrectly. I'm just going to get rid of it entirely. Okay, in a series of experiments, the U.S. Navy developed an undersea habitat. In one experiment, the mole percent composition of the atmosphere in the undersea habitat was 79% helium, 17% N2, and 4% O2. What would be the partial pressure of each gas when the habitat is 58 meters below sea level, where the pressure is 6.19 atmosphere, or 6.91? I think that's what I said. To do this, we're going to assume a 100-gram sample. If I assume a 100-gram sample, I would have 79.0 grams of helium, 17.0 grams of nitrogen, and 4.0 grams of O2. So I can kind of set it up like an empirical formula question that way. And I'm going to have to move this briefly or a little bit so I can write. Okay, so if we have a 100-gram sample, I have 79.0 grams of helium. Convert that to moles of helium. Helium is 4.003 grams per mole. 79 divided by 4.003, 19.7 moles of helium. 17.0 grams of N2. One mole of N2 divided by 28.02 grams of N2 gives me 0.607 moles of N2. And for oxygen, 4.0 grams of O2 times 1 mole of O2 to 32 grams of O2. 0.125 moles of O2. Now I'm going to go ahead and figure out the mole fraction of each species. First, I'm going to add up the number of moles just to make it easier. 19.7 plus 0.607 plus 0.125 from helium, from nitrogen, and from oxygen. 19.7 plus 0.607 plus 0.125. In total, I have 20.4 moles in the system. That means my mole fraction of helium, 19.7 moles, divided by 20.4 moles. It should be 1.3 there, but I'm not going to round to the very end. 19.7 divided by 20.4 gives me a mole fraction of 0.966 for nitrogen, 0.607 divided by 20.4 0.607 divided by 20.4 gives me 0.0298. And my mole fraction of O2, 0.125. There should be two sig figs there, though. Divided by 20.4 moles. 0.125 divided by 20.4. Again, I don't care if you don't give me the right sig figs when you're doing the calculation, but you better have the right sig figs by the end. That's what's really important. I just don't want to round you because I don't want to create round off error. 0.061. There's a 2 after that, so I'm going to go ahead and round at this point. So 0.0061 is the mole fraction of oxygen. I need to shrink these down a little bit so I can fit the rest of the work. It's so easy to hit the big eraser on here. Okay, so last part now, what's the partial pressures? Well, the pressure for helium is going to be the mole fraction of helium times the total pressure of the system. So 0.966 times 6.91, 6.68 atmospheres. Partial pressure for nitrogen, mole fraction of nitrogen, times total pressure of the system. .206 atmospheres, and partial pressure of oxygen, mole fraction of oxygen, times the pressure of the total system, 0.042 atmospheres. So the pressure of helium, 6.68, pressure of nitrogen, 0.206, and the pressure due to oxygen, 0.042. A sample containing only NO2 and SO2 has a total pressure of 145 torr. Measurements show that the partial pressure of NO2 is 43.0 torr. If the vessel has a volume of 1 liter and a temperature of 22 degrees C, how many grams of SO2 are present? So I've got something that has NO2 and SO2, total pressure of 145. Partial pressure of NO2 is this. Volume of 1 liter, temperature of 22 degrees C, how many grams of SO2? I know that my total pressure is equal to the pressure of NO2 plus the pressure of SO2, and that this equals 145 torr. Therefore, I can solve for the pressure of SO2, 145 torr, minus the pressure due to NO2, 43 torr, and I get 102 torr. I can plug that in and figure out the number of moles of SO2. I have 102 torr. Convert that to atmosphere. There's 760 torr per 1 atmosphere. Times that by the volume, 1 liter. Your gas constant, 0.08206. Liter atmosphere per mole K. And your temperature, 22 degrees C, is 295 K. And I need to check this. Let's see. 102 divided by 760 times 1 divided by 0.08206 divided by 295. 0.0055, how many sig figs? 3 sig figs. 554 moles. And this is moles of SO2. So now I can find number of grams of SO2. 0.00554 moles of SO2. The molar mass of SO2 is 64.07 grams per 1 mole. And this gives me 0.355 grams of SO2. Number 7, the root mean square speed of the molecules of an ideal gas at 25 degrees C and pressure of 2.5 atmospheres is 5 times 10 to the second kilometers per second. What is the density of this gas? So, keywords here, root mean square speed. Ideal gas at 25 degrees C, pressure of 2.5 atmosphere, 5.0 times 10 to the second kilometers per second, and I want to know density. Remember, your root mean speed is 3 RT over M. So, gas constant, temperature, molar mass. For this, R is the other version, 8.314 joules per mole K. Remember, 1 joule is equal to 1 kilogram meter squared second squared. Temperature here, 25 degrees C, is 298 K. And I'm solving for molar mass. And your root mean squared speed is equal to 5.00 times 10 to the second kilometers per second. So I'm going to change that. Sorry, in my notes, it's different in my student notes versus here. In my student notes, I have this value as a -1. And in an effort to not have to recalculate everything, we're going to change that to a -1 to match the notes. Because if you are using student notes, it is a -1 there. And that way I want to recalculate everything. So -1. 5.00 times 10 to the -6 kilometers, times 10 to the -1 kilometers per second is the same as 500 meters per second. So I've got 500 per second. Again, I do apologize. I know in the PowerPoint it said 10 to the second, but I do have it written out in the student notes as -1, so I don't want to have to recalculate everything like I just did for the last example because I didn't have it written out. This gives me 3 times my gas constant, 8.314 joules per mole K, times 298 K divided by molar mass. It is a square root here. I am going to square both sides of this equation. So I've got 500 meters per second squared, which gives me 2.50 times 10 to the 5th meters squared per second squared. This will be equal to 7,430 divided by moles. Molar mass here. Kelvins have canceled. This gives me joules per mole on this side. For units here, this gets a little confusing. Remember, joules is kilogram meters squared, second squared. So I'm going to keep that in mind in just a sec, okay? Rearrange this equation, solve for molar mass. If you solve for molar mass, that means this goes here. So I've got 7,430 joules per mole divided by 2.50 times 10 to the 5th meters squared per second squared. Now, to figure out these units really quick, this joule is kilogram meters squared per second squared times mole, that's my numerator, divided by meters squared second squared. So I see my meter squared cancel out, second squared cancel out. I'm left with kilogram per mole. And of course, I'm going to run out of room. When you solve this out, you're getting an answer here of 0.0297 kilogram per mole, which is the same as 29.7 grams per mole. Now that we have molar mass, we can use D equals molar mass times pressure over RT. So lots going on in this equation, yes, I know, but I'm going to erase this for space. And move this up here. Density equal to 29.7 grams per mole, which is my molar mass. My pressure here was 2.5 atmosphere, so 2.50 for sig figs. My gas constant, I'll have to use the other form of the gas constant, port 0.8206 liter atmosphere per mole K. times my temperature, 298K. I know this seems like a really long involved problem, but I promise you guys have all the pieces to be able to do this. 3.04 grams per mole. So in the first part of the problem, we're dealing with root mean square speed, which is modulo 6E, I think, E or F. And then in the second half, we're dealing with density correlating back to our ideal gas law, and that is from module 6C. So pulling in a couple different things here. For a spacecraft of a molecule to leave the moon, it must reach the escape velocity or speed of the moon, which is 2.37 kilometers per second. The average daytime temperature of the moon's surface is 365 Kelvin. What is the root mean squared speed in meters per second of the hydrogen molecule at this temperature? How does this compare with the escape velocity? So we're trying to reach the escape velocity or speed, 2.37 kilometers per second. Average daytime temperature of the moon's surface is 365 K. What is the root mean squared speed in meters per second for a hydrogen molecule at this temperature, and how does it compare with the escape velocity? URMS is equal to the square root of 3RT over your molar mass. Again, R is your gas constant in the form of 8.314 joules per mole K. T is temperature. The moon's temperature, 365 Kelvin. And molar mass here, we're dealing with H2. So 2.016 grams per mole. I'm going to need this in kilometers, though, for this equation. So 2.016, or not kilometers, kilograms, I apologize. Kilograms times 10 to the negative third is what I'm trying to do. 10 to the negative third kilogram per mole. Because for this equation, I need kilograms. Because I'm dealing with joules. Joules are kilogram meter squared second squared. So 3 times 8.314 joules per mole K times 365 K divided by 2.016 times 10 to the third kilogram per mole. Take the square root of that. The answer here, 213 meters per second. Remember, for these units here, this joule is a kilogram meters squared per second squared. So I've got kelvins canceling, moles canceling. Taking the square root, kilograms canceling, I get meters per second. So the root mean speed of H2 is 213 meters per second. The moon has an escape velocity of 2.37 kilometers per second. This is 11 times over, 11 times slower than the escape velocity of the moon. So a lot slower than what's required to leave the moon. A gas bottle contains 0.650 moles of gas at 730 millimeters of mercury. If the final pressure is 1.15 atmosphere, how many moles of gas were added to the bottle? Assume the temperature remains constant. So your combined gas law, P1V1, N1T1, P2V2, N2T2, says I got moles and pressure, final pressure, how many moles? Assume the temperature remains constant. And it's all in one bottle, so my volume has to stay constant too. So I must have P1 over N1 equals P2 over N2. I'm solving for N2. So P2 times N1 over P1 is equal to 1.15 atmospheres divided by 0.650 moles. Sorry, I meant to say you can convert this. So 730, I need this in atmospheres. I can either convert this now or I can convert it in the question. I converted it in the question. So 730 millimeters of mercury times 1 atmosphere per 760 millimeters of mercury, 0.778 moles of whatever gas I have. That's the total number of moles. But how many moles of gas were added to the bottle? If I've got 0.778 moles total, I started with 0.650 moles. That means 0.128 moles of gas was added. Number 10, a gas mixture consisting of 0.10 moles of N2, 0.050 moles of O2, and 0.200 moles of CH4, and an unknown amount of CO2 occupied a volume of 9.60 liters at 27 degrees C and 1 atmosphere pressure. How many moles of CO2 are in this sample? We have two different methods we can follow here. There's a longer method and a shorter method. I'll show you the longer method first, and then I'll erase everything and show you the shorter method. So method 1 is longer. Find the pressure for each one. Pressure of N2, nRT over V, 0.100 moles from N2, gas constant 0.08206, liter atmosphere per mole K, temperature 300 K, volume 9.60 liters, 0.256 atmospheres is the partial pressure of N2. Partial pressure of O2, nRT over V, we have 0.050 moles of O2, 0.08206 liter atmosphere per mole K for O2, 300 Kelvin, 9.60 liters, 0.128 atmosphere. Partial pressure of CH4, nRT over V. We have 0.200 moles of CH4, 0.08206 liter atmosphere per mole K, 300 K, 9.60 liters, gives me a partial pressure here of 0.512 atmospheres. I know the pressure of CO2 will be the difference of whatever's left. Just to move this up a little bit more so I can write. So the pressure of CO2 will be 1 atmosphere minus all the individual partial pressures. So minus 0.256 atmospheres, minus 0.128 atmosphere, minus 0.512 atmosphere. This gives me 0.104 atmospheres of CO2. Now I can use that, find the number of moles of CO2. 0.104 atmosphere, 9.60 liters, 0.08206 or liter atmosphere per mole K. 300 K. Number of moles of CO2, 0.406 moles of CO2. So that is one way to do it. That is the longer way to do it, but you can do it that way. You can find the partial pressure of each individual species, use that to find the partial pressure of CO2, and see how many moles of CO2 would create that pressure under those conditions. The other way you can do this is much faster. So if you need to write this down, please write it down. Please pause the video and write it down. The faster way to do this is to recognize that the total number of moles of this system will create the total pressure of this system. So go ahead and find the total number of moles of the system. We have 1 atmosphere, 9.60 liters, gas constant 0.08206 liter atmosphere per mole K, and a temperature of 300 K. This gives me the total moles of the system to be 0.390 moles. Total number of moles, 0.390 minus 0.100 moles for N2, minus 0.050 moles for O2, minus 0.200 moles for CH4. We have 0.0400 moles CO2. Slightly different in number, but that's due to rounding from before. So you can get from either direction. Method 1, method 2, I don't care. Whichever one you're more comfortable working. What is the pressure in a container of gas connected to a mercury-filled open manometer if the level in the arm connected to the container is 12.8 centimeters lower than the arm open to atmosphere, and if the atmospheric pressure is 749 millimeters of mercury? Hint, draw a picture. So you've got your flask, some gas inside, and it's connected to a open-end manometer. In this end is where your atmospheric pressure is. This end, your gas is pushing. It says that the arm open to the container is 12.8 centimeters lower than the side open to atmosphere. What this means is the pressure of the gas is stronger or higher. It's able to push on the mercury in that tube by 12.8 centimeters more than the atmosphere can push. 12.8 centimeters is the same as 128 millimeters. So the pressure of the gas is greater than the pressure of the atmosphere by 128 millimeters. 749.0 millimeters of mercury is the atmosphere, plus 128 millimeters from the extra from the gas gives me 877 millimeters of mercury. Number 12, the density of a halogen gas, an STP, is 7.13 grams per liter. Identify the halogen. We know it's a halogen, so that part's nice. We narrowed it down to just a few elements on the table. Density equals molar mass times pressure divided by RT. And I want to find my the identity, which means I really want to find molar mass because that's what's going to get me there. I'm going to rearrange this equation. My molar mass will be equal to my density times my gas constant times my temperature divided by my pressure. So 7.13 grams per liter times my gas constant 0.08206 liter atmosphere per mole K times my temperature STP 273 K and pressure 1 atmosphere because I'm at STP conditions. 159.8 grams per mole, which is Br2. Remember, halogens are diatomics. At least F2, Cl2, Br2, and I2 are. So molar mass is for X2. The halogen itself is Br, but it doesn't exist as Br, it exists as Br2. A certain gas has a density of 1.053 grams per liter at 25 degrees C and 752 millimeters of mercury. What is the molar mass of this gas? And just like we just solved, molar mass is equal to density times gas constant times temperature divided by pressure. My density is 1.053 grams per liter. Gas constant 0.08206 liter atmosphere per mole K. And temperature 25 degrees C is 298 K. Pressure, you can either convert separately or you can convert it in the problem. 752 millimeters of mercury. Convert to atmosphere, unless you're using a different version of R, of course. 760 millimeters of mercury. Millimeters of mercury cancel. Atmospheres cancels. Kelvins cancel. Let's see. Liters cancel. I've got grams per mole, which is molar mass. 26.0 grams per mole. The molar mass of this gas is 26.0 grams per mole. Number 14, sodium hydrogen carbonate, NaHCO3, when heated, decomposes to form sodium carbonate, carbon dioxide, and water vapor. So I've got NaHCO3 being heated to form Na2CO3, CO2, and water vapor. Balance it out. What volume in liters of carbon dioxide at 75 degrees C and 756 millimeters mercury will be produced if I decompose 26.8 grams of sodium hydrogen carbonate? Well, let's see how many moles of carbonate can be produced from this. Or moles of CO2 rather, sorry. Moles of CO2 from sodium hydrogen carbonate, 26.8 grams. Sodium hydrogen carbonate, 1 mole. Sodium hydrogen carbonate to 84.01 grams. Sodium hydrogen carbonate. 1 mole of CO2 is produced for every 2 moles of sodium hydrogen carbonate decomposed. 0.160 moles of CO2. Now I'm going to use my PV equals nRT equation. I rearrange to solve for volume. 0.160 moles of CO2. 0.08206 liter atmosphere per mole K for R. Temperature, let's see, 75 degrees C is 348 Kelvin. And pressure, 756 millimeters of mercury. Convert that to atmosphere. Gives me 4.59 liters of CO2. Number 15, ammonium nitrate, NH4NO3, molar mass of 80.05 grams per mole, can decompose explosively when heated. So I'm looking at ammonium nitrate, gives me a balanced reaction. How many liters of gas will be formed at 500 degrees C and 1 atmosphere of pressure if I explode 25 grams of ammonium nitrate? I want to know how many liters of gas. I am forming N2, H2O, and O2 gas, which means I need to find the total number of moles of the system that are produced, add all those up to find the total number of moles of the system, and use that to find the total volume. So first, number of moles of N2 produced, 25.0 grams ammonium nitrate. I'm producing 2 moles of N2 for every 2 moles of ammonium nitrate. So 0.312 moles of N2. My number of moles of O2. I produce 1 mole of O2 for every 2 moles of NH4NO3. So 0.156 moles of O2. And I don't have room up there. Number of moles of H2O, because that was the one I missed in the middle. 25.0 grams. Ammonium nitrate. I produce 4 moles of water for every 2 moles of ammonium nitrate reacted, which gives me 0.625 moles of water. So you've got these different moles, amount of moles that we're going to add up for the total moles of the system. Overall, I produce 1.093 moles of gas. Figure out your volume. 1.093 moles. Gas constant 0.08206 liter atmosphere per mole K. Temperature 500 degrees C converted to Kelvin is 773 Kelvin. And my pressure is 1 atmosphere. I'm going to produce 69.3 liters of gas. Number 16, an empty aerosol can. Empty in quotes because, well, are they ever really empty? Empty aerosol can at 25 degrees C. Still contains gas at 1 atmosphere pressure. If an empty can is thrown into a 475 degree fire, what is the final pressure in the heated can? So I'm looking at temperature and pressure, which we're assuming that means moles are constant, and we know volume's constant because we're looking at 1 can. So P1 over T1 is equal to P2 over T2. We're trying to find P2. P1 was 1 atmosphere. When it was 1 atmosphere, it was 298 K, 25 degrees C, that's my T1. And then I put it into a fire at 475 degrees C, which is 748 Kelvin. This gives me 2.51 atmosphere. So the pressure has increased by 2.5, actually. 2.5. Suppose an unknown gas has been observed to effuse 1/2 as fast as oxygen. What is the molar mass of the unknown gas? So we're dealing with diffusion. 1/2 as fast as oxygen. And I want to know molar mass. For diffusion, we're looking at rate of A over rate of B equal to the molar mass of B over molar mass of A, and we take the square root of that. Since we don't have values here, what I'm going to do is I'm going to let the rate of O2 equal 1, then the rate of unknown gas would be equal to 0.5, because it's half of it. I'm trying to solve for the molar mass of my unknown. So I'm going to rearrange this equation to get to here. I'm going to take rate of A over rate of B and square it to undo the square on the molar mass of B over the molar mass of A. And rearrange this. The molar mass of B will be equal to rate of A over rate of B, quantity squared, times the molar mass of A. Insert my numbers. The rate of A is the rate of oxygen, which we've defined as 1. The rate of B is my unknown, which is half of that, so 0.5. I square that, and I'm going to multiply it by the molar mass of oxygen, 32.0 grams per mole. My molar mass of my unknown gas is 128 grams per mole. Number 18, if 4.83 mils of an unknown gas effuses through a hole in a plate, in the same time it takes 9.23 mils of argon to effuse through the same hole under the same conditions, what is the molecular weight of the unknown gas? 4.83 mils, unknown gas, effuses through a hole in a plate in the same time that it takes 9.23 mils of argon to effuse through the same hole under the same conditions. So again, rate of A over rate of B is equal to the square root of the molar mass of B divided by the molar mass of A. The rate of A is equal to the rate of B, though. Tells me they fuse at the same point. I have 4.83 mils of unknown gas and 9.23 mils of argon. So rate of A, 4.83 mils. Rate of B, or argon in this case, 9.23 mils. My molar mass of argon, 39.95 grams per mole. Molar mass of A, no idea. Trying to find it. Square both sides of the equation to undo that square root. This gives me 0.523 quantity squared equal to 39.95 grams per mole over molar mass of A. This value is 0.274. So rearrange molar mass of A, 39.95 grams per mole over 0.274. My molar mass of A here is found to be 146 grams per mole. And our last example for the extra practice for Chapter 6, a 2.3 gram sample of a white solid was vaporized in 345 ml vessel. If the vapor had a pressure of 985 millimeters of mercury at 148 degrees C, what is the molecular weight of the solid? Well, how can we find molecular weight? That's the same as molar mass, which is grams per mole. I have a 2.30 gram sample. Now I just need to find the moles. Number of moles, PV over RT, 985 millimeters of mercury, 1 atmosphere to 760 millimeters of mercury. Volume, 345 mils is the same as 0.345 liters. Gas constant, 0.08206 liter atmosphere per mole K. 148 degrees C is the same as 421 K. 0.0129 moles. Plug that into our equation. We've got a 2.30 gram sample. We've got 0.0129 moles, 178 grams per mole. So, if you are given grams and you can find moles, you can always tell me molar mass. If that molar mass matches up to a substance, you can also then tell me the identity of that species.